Hello and welcome to a very special series of Dive into Deeptech MoSS, brought to you by Republic of Work and powered by HelixWorks Technologies. I'm your host, Aishna Gogia. For those unfamiliar with MoSS, it stands for Molecular Storage System. In other words, using DNA. Yes, you heard it right. DNA as a data storage medium. We're excited to explore the incredible possibilities of storing data on DNA for various purposes beyond digital archival. Throughout this series, we will be talking to experts and innovators in the field to get their insights and perspectives on the potential of using DNA data storage. We will introduce the basics of DNA data storage, discuss various technologies used to store data on DNA, address the challenges in using DNA as a form of data storage, and explore its potential applications in different industries. So join us as we dive into the exciting world of DNA data storage and explore the potential of this revolutionary technology. I'm so excited to bring another episode of this series today. We are joined by Dr. Raja Appuswamy, an assistant professor at the Data Science Department at EURECOM in southern France. He's currently working at the intersection of computer science and biology. In today's episode, we'll be talking about some of the exciting projects being undertaken by Dr. Raja and his team, from OneOligo to MoSS. Welcome to our show, Raja. We're so delighted to have you on the pod.
Hello, Ishna. Thank you very much for having me here. I'm really excited to be a part of this podcast.
So I was browsing through your EURECOM's website and I loved your brief bio there, especially the line which said, "I'm presently daydreaming about several things at the intersection of computer science and biology." Could you tell me a bit about your work and how did you transition into DNA data storage?
Yeah, sure. Yeah, I think that's the perfect way to actually, because I really am dreaming there's a specific reason why I actually wrote it that way, and it might seem like a bit funny, but the truth is that I'm not a biologist, and that's why I said I'm daydreaming, because quite often when I actually look at problems at the intersection, I often find myself, really daydreaming about the problem without the biological background, and I have to go and talk to biologists to get more background. But anyway, that's my background. That brings me to my background is actually in computing systems. So I work on large scale computer systems. Any application, any area which actually stores a large amount of data, you have two main problems when it comes to data. You have to store the data first, and then you have to process the data. And my work tends to focus on both these aspects. So how do you store data efficiently, both for quick access and for very long-term storage? And how do you process data efficiently in terms of, if you have huge petabytes and zettabytes of data, how do you very quickly analyze the data, process the data? So I focus on both these aspects in computing systems, and I look at variety of different applications with respect to this, right? So that's my background.
And what were some of the motivations that actually attracted you to pursue DNA data storage in specific?
Yes, indeed. And I think that's a very good question. And I think DNA data storage is really my primary entry point into biology. So before DNA data storage, my whole line of work, my PhD was actually in data storage. So I actually built storage systems that could store large amounts of data, starting from a single computer. I actually worked on the Minix operating system, which some of your listeners might actually know. It was an operating system designed by Andrew Tannenbaum, and he's kind of godfather in computer systems field. And if Minix is the operating system that kickstarted everything, so if Minix was not there, Linux wouldn't be there. If Linux is not there, no laptops, no desktops, no mobile phones, right? So I worked on Minix during my PhD, and I designed the storage system for Minix. And after that, I was in Microsoft research for a while, where I was with the group that actually designed a very large scale cold storage system at the time based on hard disk drives for storing data that was generated within Microsoft. So I was actually observing the team. I was actually learning from the team. And that really made me get very interested in the problem of extremely long-term storage. I originally focused on very quick data accesses. That was what my original focus was on. But then once I observed the problems related to long-term storage, I started getting much more interested in it. And the very first venture that I actually did in long-term storage was not on DNA. I actually worked on researching traditional media for long-term storage. Things that you might know, like, for example, hard disks. So if you have to store data on hard disks, and if you want to store, massive amounts of data on hard disks, how do you actually build a large scale storage system with hard disks such that they consume very, very low power? And how can you actually store data on such a system and directly do analysis on such a system? This is one of the things that I started looking at. And from there, I also started investigating tape. Many of the listeners might not know that tape is actually a very popular and, in fact, the most widely used storage medium today for storing data, long-term data storage. So if you look at storing data for more than 10 years, the gold standard in the storage industry is actually tape. And so I also looked at tape for a while. And while I was working on these systems, certain problems actually started coming out. And these problems really made me interested in looking at DNA.
So, while we're talking about the problems, what are some of the problems in the traditional methods of data storage, like you mentioned, disks or even magnetic tapes? I mean, they are probably a lot more cheaper. And what benefits do you see in using DNA data storage over other traditional methods of data storage?
Yeah, indeed. So they are definitely, you're absolutely right. So they are definitely way cheaper, especially compared to DNA today, right? They're several orders of magnitude cheaper than DNA. But there are some fundamental problems that we have today with current storage media. So the first problem is what we refer to as media decay. So pretty much any storage media that you have today is going to basically decay and die within a particular period of time. So if you look at hard disk drives or flash or solid state drives, the typical duration is 5 to 7 years. You can stretch it a bit, but that's usually the duration. So after 5 to 7 years, the media is going to start rotting away, and whatever data you store on the media is going to slowly die and decay. With respect to tape, it's a bit longer. Tape can actually last for 20 to 30 years, but that there is a finite limit in terms of, once again, there's 20 years is probably a limit in terms of how long you can actually store data today on tape. So this is one thing that we refer to as media decay. That's the first problem. In fact, you might say that, okay, so 20, 30 years sounds fine. I mean, maybe that's actually long enough for me. Yeah. But it turns out there are many, many people who are, looking at storing data for centuries, right? And potentially some people who are looking at storing data forever. I'll talk about some of these people later during the podcast. So it really is a problem. If you are one of those people who want to store data for a very long time, 20, 30 years is a very short time period for you. So, and it's not sufficient. But the problem gets worse. So this is a media decay problem. And even if you are one of those people who thinks that 20 years is fine, it turns out the lifetime is really not 20 years because of a second problem that we actually call media obsolescence. Now, tape is basically similar to any technology. Tape technology also improves. And tape is on this beautiful 33% improvement trajectory every year. So what this means is every year, the amount of data that you can store per a square millimeter or per areal density of tape, the amount of data that you can pack in a small region of tape, it continues to grow at 33% per year. The issue with this might sound like good news, but the issue with this is that every few years, if you just wait for 3 years or 5 years, you will be able to store double or quadruple the amount of data that you can store with half or 1/4 of the amount of tape drives that you actually use today. And when you store data in tape, you have to store those tape cartridges somewhere. And storage is actually a premium commodity in a data center. So there is the very big motivation for people to migrate from what they are storing right now to a newer generation of tape to save space. There's another reason why they want to migrate. I told you the technology improves every few years. The tape industry has the standard called the linear tape open, LTO standard. And once you store data on tape, in order to read the data back, you need to use something that's called a tape reader. It's a specific device that can actually read data from tape. It turns out that tape readers maintain backwards compatibility only up to 2 generations backwards. And 2 generations, one generation typically is around 3 years. So 2 generation typically is around 6 to 7 years. What this means is if you store data today, 7 years later, that's basically the limit at which the tape reader that comes out 7 years later, that's going to be able to read your data that you store today. But any tape reader that comes out after that is not going to be able to read the data stored on your tape drive. So this is what we refer to as media obsolescence, meaning the data is on the media might be fine, but you just cannot read the data of the media because the reader is not there anymore. So this is the second problem. And what this really means is you have a huge motivation to move the data out of the tape within 5 to 7 years. And that basically brings the limitation of lifetime, right? So within 5 to 7 years, you have to move the data out. And this, in essence, is the problem with the media that we have today. It's the constant migration that you have to do every few years between, old generation of media and a new generation of media.
And is there a stat about, around the data that is lost because of the fact that the media has become obsolete or because of the media decay, and how much the companies or how much data would we be losing if we weren't, if we weren't taking care or if we weren't actually updating our media storage systems every now and then?
Yes. So there is in terms of companies and enterprises, there is information we do have. People are starting to gather information now about the problems that they are facing in terms of migration. So, but there is a very, very clear example that shows how this is becoming a problem. And the example is coming from Hollywood. So there are movie archives in Hollywood which are tasked with preserving movies forever. And these archives, they have to store all the movies that are made in Hollywood. And over the past few years, we have actually switched to very, very high definition cameras that can actually shoot, videos with very high quality. And what this really means is these digital cameras are producing films. A single film can be several terabytes in size. And now the Hollywood archives are storing these terabytes of data for posterity, right? They have to keep it forever. And they have run into this problem. And every 5 to 7 years, and naturally they're using tape because tape is the cheapest way to store data today. And every few years, they have to migrate the data out to a new generation of tape. And because of this, the fact that it costs millions of dollars to do this, to migrate and do a forklift upgrade, they've basically announced that we are going to stop archiving all movies. We are not going to archive independent productions. We are not going to archive small movies that are not basically making it, many people are not going to be, that's not going to be a huge demand for those movies. So many of these independent works, many of these niche works are going to be lost. And they've already said that there is a dead period that is going to start probably in the 2000s, right? So it's already started, where we are going to lose a lot of, heritage in terms of movies that are basically being made. It's just going to be gone. They're not going to save it. And I think that's a warning for all the enterprises out there today, because everybody's going crazy after AI, machine learning, and data analytics, and everybody is gathering data like crazy. And the moment you use your data in any machine learning model or in data analytics, and you make a decision, a business decision based on it, in most cases, you're obligated to keep that data to meet legal and regulatory compliance requirements. In case somebody comes back and sues you, you need to be able to produce the data to identify and verify why you made the decision that you made, which means you need to keep the data for a long time. And I think enterprises are very, very soon, if not already, they are going to face this crunch in terms of the data migration problem, right?
Yeah. So then how does DNA data storage come in, and what would be some of the benefits that immediately in terms of, database archival that DNA data storage might be able to offer over traditional methods then?
Yeah. So that's precisely why I got interested in DNA, is because of the fact that it actually solves both the media decay and media obsolescence problems. It solves the media decay problem because, as others in your podcast have already mentioned, the DNA is actually a very, very stable molecule, right? And once you actually store it in a inert environment at room temperature, there are ways in which you can store DNA such that it can actually last for millennia without any problem. So there is really no media decay per se, right? So you're looking at storing data for thousands of years on DNA. There's no problem. Media obsolescence is also not an issue, because unlike current media, where I told you that the reader is actually tied to the media. So tape requires a tape reader, hard disk require a hard disk reader. DNA is interesting in the sense that the media is decoupled from the reader. So to read the data from DNA, as other people in your podcast would have already mentioned, you need a sequencing machine. And we know over the last 40, 50 years that there has been an improvement in sequencing technology, a rapid improvement in sequencing technology. And we have had many, many different sequencers come out in the market, come out from research, starting with Sanger sequencing. And then we have Illumina's sequencing by synthesis. Now we have nanopore long read sequencing and PacBio long read sequencing. There are so many different technologies, but the underlying DNA remains the same. And this is really interesting because once you store data on DNA, as long as you are able to sequence the DNA, it does not matter which sequencing technology you use. You can use any technology. And that basically solves your media obsolescence, because you know that once you store data, you will always be able to read it.
Yeah. That actually is a good segue to sort of speak about the projects and different projects and how they're kind of working on different aspects of DNA data storage as well. So EURECOM is involved in a couple of projects beyond, it's all in the scope of digital security, data science, and communication systems. But what areas of DNA data storage is your department most interested in? And what are some of the projects, we'll be talking about them from OneOligo to OligoArchive and MoSS. Like, what are some of the projects that your lab is working on?
Yeah. From EURECOM's point of view and from my point of view, particularly, we are very much interested in viewing DNA as a storage medium, right? So what this means is connecting my background with DNA, you can already see what I want to do is basically build everything that is required in order to make DNA work like a hard disk or work like, I should say, that's probably a better analogy. And what this really means is you want to be able to store data on DNA very, very reliably. And even if there are errors when it comes to synthesizing and making the DNA or sequencing, reading the DNA, you want to be able to store data in such a way that you can mask those errors and you get 100% reliability when it comes to storing the data. That's one of the focuses of my PhD and my master's. I focused on reliable data storage using conventional media like tape and hard disk. And now I'm bringing that expertise over to DNA and looking at how do you reliably store data using DNA. That's the first aspect. The second aspect, of course, is the fact that I told you I want to view DNA as a tape. What this really means is we want to actually offer some kind of abstractions over DNA. So when you store data on, for those of you who don't have the computer systems background, when data that's stored on tape, you can read data using what's called a block address. So tape is basically divided into fixed size blocks. And you can say, okay, I want block 0 or block 20 or block 30. And this kind of abstraction allows you to view tape in the collection as a collection of blocks instead of having to view it as, as something else, right? So, and using this block abstraction, now you can build other abstractions, the higher level, which is cool. Now you can build files and directories. You can say file 1 is stored in blocks 0, 10, and 20. File 2 is stored in blocks 20 and 30, so on and so forth. You can start collecting files together into directories, and you can start building these nice higher level abstractions, which are then used in normal computers and presenting tape as a normal device. And that's exactly the second aspect of DNA storage that my group focuses on, together with other collaborators of OligoArchive, is on providing this kind of addressing and providing these kind of abstractions that allow you to address data on DNA using block addresses so that you can selectively retrieve blocks or do this kind of access paths, right?
Yeah. And that is, I think, one of the first things that you also worked in, which was reading DNA data, which is very error prone. But you've developed protocols around it, which kind of rely on metadata and make the entire process less error prone as well. Do you want to talk a bit about your projects, starting with either OligoArchive on OneOligo and then talking about all the cool things your research department is involved in across the collaborations that you've done?
Yeah, sure. So basically, we started we're a part of OligoArchive and we started it back in 2019. But yeah, when we started OligoArchive, as I told you, my focus was on these two things. One of the very first things that we actually developed, because I have my leg in, so one of the things I told you was not just in storage, but actually also in processing the data. So one of the problems, the very first problem that we actually hit when it comes to DNA storage was we did a simple experiment with DNA storage. We stored some data on DNA and then we wanted to read the data back. So we worked with our biologist in sequencing the DNA, and our biologist gave us back this set of this. He gave us this file. The biologist we are collaborating with is Dr. Pascal Barbary, who's here in CNRS. He gave us this file, which is basically a huge collection of strings. There were several hundreds of millions of strings in the file, and he basically said, this is what the sequencer produces. We stored a set of, let's say, 10,000 oligos in 10,000 strings that originally generated. And now we have a collection of 100,000 or 100 million strings from which we have to infer the original 100 strings that we generated. Now, what I'm just assuming here that the listeners actually already heard the podcast or DNA storage. If you're not aware, here's a quick overview in the sense that to store data on DNA, you would take bits, you would convert it into strings, which represent your DNA sequences. DNA sequences are really, for the simplification, we can view them as a collection of ACGTs, string of ACGTs. You have to take your bits and you have to map them into strings of ACGTs. You cannot store it all in one long string because current synthesis techniques are limited to 300 or 400 nucleotides at best, and beyond that, the quality degrades. So you have to convert any reasonably large file into a collection of these strings. And that's why I mentioned that you would, during the writing part, when you store it on DNA, you would generate these strings. Then you would do the synthesis with a company like Helix, for example. And then once this is done, to the data back, you would sequence the DNA. You would get back another set of strings. These strings do correspond to the original strings that you generated, but they're also very, very noisy. So you can get many errors and you can get many, many copies. So every original string can be copied 10 times or 100 times, and it varies, right? So now it's your job to figure out what the original strings are from this jumble of strings that you have now. And this, in essence, is actually a database problem, because now you have a collection of strings, and what you want to do is you want to cluster the strings, and you want to find out a consensus string from each cluster. And there is, in databases, we have this algorithm that basically called edit similarity join, which is basically you take a table or you take a column of strings, and you want to find out which are the strings that are most similar to each other. And it's exactly the same problem here. So what we realized was it was the database problem, the query processing, the join processing problem here applied to a huge data set, 100 million strings. And we realized that the current solutions that database people actually have, they do not scale well to this large collection of strings. So this led us to implement, something what we call the one join solution, which is basically an algorithm that allows you to perform this clustering and consensus using not just CPUs but also GPUs, so graphics processing units, which are now the workhorse for machine learning. So by using heterogeneous combination of different devices, we're able to really rapidly analyze the reads that you get from the sequencer and infer the original strings. So this was one of the very, very first problems that we actually hit in terms of working on the read. And when we built this one join algorithm, we realized that there was an upcoming standard, and here's a shout out to Intel for developing the standard. It's called OneAPI, and it's a standard that allows you to program heterogeneous hardware without any vendor locking. And that's pretty amazing, because so far, if you wanted to work with GPUs, you had to work with, let's say, from GPUs from one vendor like AMD or NVIDIA, and you had to use one particular programming tool chain like CUDA or HIP to program those GPUs, and the code that you wrote would not work across vendors. So Intel is really working hard now on making it possible for you to write programs that can work on any possible GPUs from any vendor. And I think this is a very, very powerful initiative that's come out in the last few years. And we developed one join using one API. And that's why we call this project OneOligo, just as a pun, because it's one join, it's one API, so it's one and everything. So it's OneOligo as a thing. And Eugenio Marinelli, my student who worked on this, he actually ended up winning the Intel Great Cross Architecture Challenge for this work. And he went to CERN for an internship. So this was really, I think it was a pretty, very, very cool project that kind of brought together technologies from high performance computing and databases and mashed them together to solve a problem in DNA data storage. So that was the very first thing that we did.
Yeah. What are some of the other highlights from OligoArchive then? I know there are loads of collaborations that or like pilots that came out of OligoArchive. Do you want to talk a bit about DNA for DNA, or the project that you're doing with the was it a Australian videographer or filmmaker?
Yeah. So that's, I think, one of the best things that came out from OligoArchive for us was actually all these pilots, and I'm very, very proud of these pilots. So there are 3 pilots which we are actually working on in OligoArchive. The very first pilot is actually together in collaboration with the Danish National Archives, and the Danish National Archives have this beautiful use case where they're actually preserving hand-drawn paintings of a very, very beloved Danish king, which done about 600, 700 years ago. So they have a hand-drawn physical painting. They have digitized the painting now, and they want to put the digital image, which is the digitized version of the physical painting.
Yeah.
And this, in essence, basically is, sort of maps you back to the problem that I talked about, right? So they have the same issues that I talked about in terms of tape. And here is something, here you have a digital file that they want to preserve forever. There's no expiry on this thing because it's a part of the cultural heritage. And so when we talk to them, we realize that it's a very, very cool idea. It's a very cool use case for OligoArchive, use case for DNA storage is to apply DNA storage to digital preservation. And while we do it, it also showcases another thing. The fact that DNA storage is actually, DNA solves the 2 problems that I told you about, which is media decay and media obsolescence, but it's still only a small part of the overall digital preservation lifecycle. Okay, because there are several other issues that come in digital preservation that DNA does not solve. A very good example of that is what we call format obsolescence. Let's take this example, and here is a perfect example for showcasing this. Is we have the photograph of the painting done by the Danish king, and the photograph is in a JPEG 2000 format, file format. Okay, you store the photograph today on DNA. The DNA is perfectly fine. 1,000 years later, somebody takes the DNA and sequences the DNA. So you don't have decay, you don't have obsolescence. Now somebody takes the reads that they get from the DNA and they ask the question, okay, now I have sequenced the DNA. How do I get the original file? So the question is, I told you that we are developing encoders and decoders that basically allow you to store data on DNA, for example, one join algorithm and all that. So how are you going to run the encoder and decoder 1,000 years from now? How do you even know that the code, the language in which you have written the programs is going to exist 1,000 years from now? That's the first thing. Right? Another problem, say suppose by some hook or crook, you're able to run them, you get the file out, right? And now you have a JPEG 2000 image. How do you know that JPEG 2000 is going to be readable 1,000 years from now? How do you know that the format is going to exist, right? So collectively, we refer to this problem as format obsolescence. The fact that your data is there on the media, you're able to read the media, but you cannot make sense of it, okay? And this problem is not solved by DNA storage. And so what we actually did as a part of the Danish National Archive project is I have collaborated here with some experts from digital preservation, and particularly one expert here who has a startup called Upalia. So this company is actually working on using analog media like paper, like microfilm or cinema reels to store digital data. So just like DNA, they can use analog media to store digital data. Okay. And this is cool, but the problem that they have is the fact that analog media has limited density. Just like tape, analog media has very, very limited density. So what we actually had, an idea that we had, something that we started working on that's still ongoing, is basically you store the data on DNA, and then you store all the other stuff that you need to decode the data back. You store it on analog media like film or on paper, and you store the two together as a unit. So this is pretty amazing because now you have biological media, DNA, you have an analog media like film coming together to store digital data, right? And so we are working at the end-to-end cycle to solve format obsolescence together in the context of this Danish National Archive. So this is a collaboration with that, with Upalia, with the Danish National Archives that's basically ongoing. That's the first pilot. We have another pilot, which is basically in collaboration with a bunch of artists and researchers from Australia. This is Dr. Louis Karam. And there we're actually looking at storing a film, which is once again, it's actually an iconic movie by a very famous artist called Malcolm Legris, where what he tries to do is it's a very interesting, I think it's one of the very first attempts to actually use light projection to create a cinematic effect. And he uses his own body to actually create various, projections based on the strobing light that you can actually see in the movie. What's unique about this movie is that the movie is not just a visual for someone to see. The movie is actually kind of, it's kind of an instruction for someone to replicate. And it's like it's kind of an imaginative trigger for someone that tells someone to go and play with light and how to play with light. And that's why this movie became very famous. And now you have this thing, you have a movie that an artist created where he shows you how he is playing with light. And how do you actually transmit this instruction? What you want to show is not just the movie, right? What you want to transmit is the instruction, is this art. The fact that the art is the way in which he did it for someone else to replicate it 100 years, 200 years later, right? So once again, this goes way beyond DNA storage, right? So DNA now becomes a medium in which we are actually storing the movie. But in addition to the movie itself, we're also storing instructional material, right, that actually allows someone in the future to watch the movie and then recreate the movie for themselves. So this is, once again, I think a pretty cool project that showcases how DNA can be used in digital arts, for example, right? Yeah. So that's the second one. And the third and final pilot that we have is yet another amazing pilot that I'm super proud of, is in collaboration with the European project called Old Europa, which is actually focusing on preserving the digital cultural heritage of smell. So we know that certain fragrances are associated with certain things. Frankincense, for example, is a very, very popular fragrance that has culturally historic significance, right? And it's widely used in many, many places, including religious places of worship, churches, so on. So if you want to preserve the frankincense itself, and frankincense is actually such a popular fragrance that there is a big group of people that are actually working on, making sure that frankincense used everywhere is the same and so on and so forth, standardizing it, things like this, right? So if you want to preserve it for somebody 1,000 years later, how do you preserve smell? And that's what OligoArchive focuses on. How do you preserve smell? How do you bring back smell from 300 years, 400 years ago to life today for studying various things? And one of the cool things that actually did, for example, is when you go to, they have this cool app, a cool thing that you can do when you go to Amsterdam. You can actually, when you go touring Amsterdam, they give you this small smell card, which you can use to sort of remember various places that you have visited based on the smell of those places. And so smell is a very potent trigger for memory also, right? And so this OligoArchive project focuses on preserving smell. And we, through OligoArchive, we are actually working together with them on a pilot with them, where we're taking frankincense, a lot of cultural information about frankincense, the chemical molecules that are responsible for the frankincense smell, together with a whole lot of data, and we are storing it on DNA. And once again, this is like an intergenerational transmission medium, DNA, that we are using to actually meet a larger goal, which is the cultural preservation of something more significant, right? So those are the three pilots that we are working on. And underneath all these three pilots basically sits our robust DNA data storage system that we actually built in the lab.
Yeah, no, it's really interesting to hear the kind of projects you've undertaken, because it's not just about making a technical breakthrough, but it's about how do you that with other areas of life, whether it's, preserving something like a memory, even like a photograph or a movie for, prolonged purposes, or for it to go down generations, or even just, like you said, storing your cultural heritage as well for somebody to remember it down the line when maybe these things are not around, or, we've kind of lost the essence. But you're also involved in some of the other projects around DNA data storage, and one of them is MoSS. What's happening there? What would be your comms involvement in the project? I actually recently read one of the papers that was published introducing quite a few new concepts, where you've proposed a new framework around composite motive-based DNA storage systems, which utilizes pre-designed motives as building blocks to decrease synthesis costs by increasing logical density. Do you want to talk a bit about the concept that you've been working on, the motive search, which is a novel consensus caller? And I'll let you explain all of us, if you want to walk us through the new workflows and tell us what it entails.
Sure, yeah, absolutely, yeah. So I think the link between OligoArchive and MoSS is really OneOligo, and I think we had the right succession of things, right? So I told you OneOligo was this one join algorithm that we built, and when we built this algorithm, one of my PhD students, who's actually working with me now, she realized that this kind of which allows you to compare strings, it's not something that's only used in DNA storage. Actually, it turns out that there is a whole field of that's called computational genomics, which actually looks, developing tools and pipelines and algorithms that allow you to analyze genomic data. And by genomic data, I mean when you look at, when somebody has predisposed to getting some type of cancer, or when someone does have cancer, what is the chance of what is the chance that their cancer is going to progress a certain way, or what is the probability that they're going to respond well to a particular treatment? All of these questions are now basically handled by genomics, which is basically a field that analyzes your, computational genomics particularly is something that analyzes your DNA and trying to find out variations in your DNA that are responsible for disease, and how different variants correspond to different treatments. So one of the things in this particular computational genomics field, whenever you look at processing data for genomics, is what's called sequence alignment. It's an algorithm that sits at the heart of the whole genomic data analysis pipeline. It's the very first step that you do. And it turns out sequence alignment is basically the problem where somebody, you need to analyze the DNA of someone, take their DNA, you take a blood sample, extract the DNA, sequence the DNA, and from that point, you need to align the reads that you get from the sequencer to a reference genome. So there's a bit more detail involved here, which I don't want to get into because the readers might not be working in this. But in essence, what I want to share here is that edit similarity problem that we found in one join, which was very useful for DNA storage, we realized that same problem exists and same problem appears in sequence alignment in computational genomics. So my student Yiching Yang actually worked on developing a new sequence aligner that's called AxelAlign in collaboration with a startup here called Axelo. And this sequence aligner uses some very clever algorithms, randomized algorithms, which were also used in the context of OligoArchive to actually accelerate sequence alignment for computational genomics. And while we were doing this, we also realized that this algorithm is something that's so universal, right, that you could basically apply it to many different problems. And one of the things that came out of OligoArchive was the fact that, we actually demonstrated, as I told you, with the pilots and with other stuff, that you can reliably store data on DNA. And Helix actually managed to basically showcase their enzymatic synthesis platform, the point of it, the power of it. And through this, they are able to basically move ahead and secure the EIC transition funding for Project MoSS, which we are a part of. And so our role in MoSS is really to actually investigate this problem, the sequence alignment problem, or this edit similarity problem, I should say, which is similar in one join and in sequence alignment. We want to bring that to the new synthesis platform that Helix is actually building. So that's what basically is our focus in MoSS, and that's the starting point for motive search. So you mentioned a little bit about the new paper. I think that new paper, which is on bioRxiv now, summarizes what we have basically done so far in MoSS. And MoSS takes a very different approach towards DNA storage, unlike OligoArchive, where, with Helix and MoSS, what we are viewing DNA as is not a collection of individual nucleotides, but rather if you actually view DNA as basically an assembly of shorter strands of DNA, which we call motifs. So imagine you have a library of very short DNA strands. These are called motifs. And now when you want to store data on DNA, instead of going and, sort of making random DNA strings, you start from this library of short DNA strings and you make longer strings by attaching one small DNA string to another small DNA string. So it's an assembly of small DNA strings that you want to do to build the library, to build your oligos for DNA storage. The reason why Helix wants to do this is because when you have a small library to begin with, it's very easy to actually automate things compared to having to randomly write DNA strings. That's one reason. And the second reason, which is the core of the work that we are doing now, is that when you have a small library, you can actually, sort of use what we call sequence multiplicity, which is the fact that when you make DNA, you're not making one strand, you're making multiple strands. And instead of storing using the same short strings in multiple strands, these motifs in multiple strands, you can use a mix of them. And in a nutshell, I think you'd have to go into much more detail to understand this, precisely with a figure and everything, but which is all there in the paper. But in a nutshell, what we are trying to do is, by using this mixture of combination of things, we are actually adding one more dimension to DNA storage. And this is what we refer to as the logical density, which allows us to add more data, store more data by actually using a combination of things, but rather than using just individual things. Okay, so that's the nutshell. But in essence, we have a new way of assembling DNA strings. Helix is going to then take these, the DNA strings, and then they are going to actually assemble them using their new, assembly mechanisms, which is basically the bridged oligonucleotide assembly. So this is a new enzymatic ligation chemistry that allows them to build these strings, build DNA strands very efficiently using these short motifs. And now comes our point where, once again, you have stored data on DNA. Data is basically stored on DNA. Each DNA is a combination of these short motifs. And these short motifs have been ligated using a specific chemistry, new chemistry, which means there are a lot more errors. And now we are back to square one, where when you want to read the data back, how do you recover back the original strings from these error-prone DNA reads that you have? And this is where, once again, the whole edit similarity algorithm applies here. And so my student Yi-Ching Yan and I, we have been working on motive search, which is basically the third application of the edit similarity join algorithms that we have used, right? So the first one was one join, second one was accel align, and now the third one is motive search, where at the core of it is the same algorithm, but we have to tailor and customize this algorithm to the new synthesis approach and to the new DNA design approach. So that's what motive search does.
Okay. It's basically going to make sure that the recovery is successful despite the high error rate, and it will basically be able to eliminate all the noisy reads. Yeah.
Exactly. So it's going to take the noisy reads, and it's going to, even though you have errors in the read, it's going to actually be able to recover back the original data, even though you have the errors. And it does this by very cleverly exploiting the fact that your DNA is not a collection, it's not a random set of nucleotides, but it's actually a collection of short motifs that's taken from the library. So it actually uses the knowledge, right? The fact that DNA is actually an assembly of short motifs to transform the problem into an alignment problem which is what the edit similarity algorithm is used for. And so we connect everything together once again, and we build a custom solution specifically that we know that we parameterize it in such a way that it's guaranteed to recover the data, even if the helix synthesis.
I'm just going to make a little quick shout out. When Raja says helix, he means helix works. But in
Yes.
terms of cost comparison, do these new techniques hold the potential to bring down the cost further? Do you think the introduction of motive search or the likes, within this paper as well, what kind of potential do they hold in bringing down the cost further?
Yes. So I think the cost improvement is really going to come from multiple angles, right? So the first one is the fact that because you are able to actually using motives, using the short connection of strings as building blocks, I told you that you're able to automate things easier. And automation naturally means you will be able to manufacture DNA using fewer reagents, using fewer raw materials, which means that's the first factor that leads to improvement in cost. The second factor is going. I told you that by using a combination of motives rather than just individual motives, we are introducing a new dimension to DNA storage, which allows us to scale what we call logical density. Logical density is really how much data are you adding during every synthesis run. So whenever you want to add one motive to another motive, how much data are you actually adding by every synthesis run, right? And by using this, combination of motives, we can increase the amount of data we add per cycle. What that means is you reduce the number of cycles, and naturally this will reduce the overall cost. So that's where the second reduction in cost comes from. And the third point where the cost reduction comes from is motive search, which actually is customized to HelixWorks synthesis. We have configured it, we have built it so that it can detect, it can recover the data despite the errors, and which naturally means that you can now do sequencing, without having to have a very, very high coverage. And by coverage, what I mean is when you do sequencing, you're reading the components of each DNA strand. And normally you would not read the DNA strand once. You would read it 10 times or 20 times, because each time you read it, you're making errors. And the hope is that across all the reads that you get, you can sort of the errors is kind of distributed and you can still recover the original. But with motive search, you'll be able to read the DNA way fewer times, probably even once, that's where we are trying to get to. And this way, the cost of sequencing is also going to go down. So you get this triple whammy, right? So we are reducing the costs on all three fronts. The precise numbers are very, very hard to gauge because these are, we are still at a stage where we are optimizing various things, right? So every single stage of the MoSS pipeline. So hopefully in the near future, we'll be able to come up with really concrete numbers. But for sure, I think we can easily reduce the cost by 10 to 100-fold without any problem, I think.
That actually brings me to sort of the next section where let's talk a bit about the barriers and challenges, that we are currently that are currently hindering the progress in this field. So the price of DNA synthesis is still more expensive than tape. The automation or performance of synthesis and sequencing is also kind of just coming up now. But again, like you've mentioned throughout the podcast, DNA not necessarily solves the problem of, does not solve media or format obsolescence. So, what kind of improvements are we expecting to see over the next couple of years in the near future? And if you want to talk a bit about what challenges do you think are hindering this progress right now, and we might be able to solve them in the next couple of years?
Yeah. So, yes. So, as I told you, I think technologically, from the DNA point of view itself, right? So, from the DNA point of view itself, I think you nailed it perfectly. I think the major bottleneck right now is the synthesis cost, which is writing the DNA, so synthesizing and manufacturing the DNA, right? So we need big breakthroughs in synthesis chemistry, and I think HelixWorks approach is a very, very good starting point. And I think if they are able to scale it down into picoliters and into very, very low concentrations, they have the potential to really scale the cost down at least by 1,000-fold or maybe even more. And then there is room for further improvement there, right? Because I think right now we are looking at 6 orders of magnitude difference between DNA and tape. So that's a million times more expensive today, DNA. So we have quite a bit of way to go before DNA can become cheap. So on the DNA front, synthesis, that's the main bottleneck, at least from my viewpoint.
And what about sequencing? Do you not think sequencing would be like the decoding part, reading the data from the sequencer as well? what kind of breakthroughs do you think we need on the sequencing side to kind of bring that up to speed as well? I know a lot of times we talk about DNA data storage being for cold archival, but at some point, if you have to read the data as well, what do you think that, we could do in terms of the sequencing side to bring up that speed as well?
No, that's a very, very good question, right? So the sequencing compared to synthesis it's improving pretty rapidly. So now, 20 years ago, it used to cost $1 billion to sequence the human genome. And now we are at the point where we are actually at a few $100, $200 or something like that to sequence the entire genome. So it's really rapidly advancing, right? So the cost of sequencing is dropping rapidly. But I think there, once again, you hit the problem, right? So the issue with sequencing, once again, I think as the technology matures, the cost is going to fall more, but definitely throughput is going to scalability is going to become a problem. And I think that's where you need algorithms like OneJoin, right? And so as new sequencing technologies come out, you need to study their error characteristics. You need to study design decoding solutions, clustering solutions that allow you to sort of keep pace with the rate at which these sequencers can actually produce the reads. It's an interesting challenge, but I don't think that's at this point yet. It's definitely something that that needs to be worked on, because I think, if you just wait for synthesis without focusing on sequencing, we might end up at a situation where, synthesis scales and then we end up with the read bottleneck, right? So people should work on that as well. But I think even if we had a sequencing breakthrough today, it's unlikely to reduce the cost of DNA storage overall, right? And that's why I said that the fundamental bottleneck is on synthesis.
Synthesis, yeah. And what do you think the timeline looks like if you're thinking of scaling DNA data storage from lab to market?
Yeah, so it's hard to predict these things, but I think one of the good things is that there is a huge consortium of people who are now very interested in this subject. There's the DNA Storage Alliance that has been formed, and many people are onboarding, and many people are, the new startups are being established every few months, right? So, and the space is seeing a rapid growth. So it's my hope that hopefully we will actually see DNA storage becoming much more cost effective and potentially as not as a substitute for tape, but at least as a layer behind tape. We hope we should be able to see something like that in the next 5 to 10 years. So that would be the most optimistic guess I would have. Anything shorter than that, I think, is just impossible, at least from my viewpoint.
Yeah. No, something that you mentioned now as well, and I think we're kind of observing it a lot more than before, is the collaboration that's happening between industries, SMEs, and academic partners as well. And just like yourselves, most researchers are on track to collaborating with industries or relevant academic partners across the continent. Can you talk a bit about how do you collaborate with all these people? How, even with the Australian partnership that you have, what was, how did you reach out to the people, or how did they find out about your work, or how did that partnership, happen over a period of time?
Yeah, I think that's basically the way, because DNA storage it's a very interesting topic. It's super interdisciplinary, and so there is, you find yourself often, going to conferences and going to venues which have nothing to, at least in my case, it had nothing to do with my background. And one of those conferences was actually the International Conference on Digital Preservation, which is hosted every year by the Digital Preservation Society. And there you have museums, archives, artists, a whole lot of people. Anybody who was pretty much interested in digital preservation is there, and they're talking about all the problems that they are facing. And I managed to basically get there in 2019 and give a 2019 or 20 and give a presentation there on our work in OligoArchive. And many of the contacts that I acquired basically came through that conference. And in the case of Ode Europa, the one where we are working on preserving smell, one of my colleagues, Professor Rafael Transi, he's actually a part of the Ode Europa consortium. And he was the one who actually, when during one of the meetings, we said, I'm working on preserving smell, you're working on preserving data on DNA. At some point, we should actually put the two together. So it was an internal collaboration that actually came out. So my general advice actually for pretty much, my general suggestion, right? It's basically for people working on DNA storage to really reach out to this broader community of people who are working in digital preservation, because they really give you a totally different perspective on what other problems there are, how DNA can fit into a broader scope of, long-term data storage, long-term data preservation. And also potentially this gives you companies that are working on DNA storage. This gives them access to their very first pilot testers and customer base, which is actually the museums and archives who are really looking for solutions for long-term data storage, right?
No, absolutely. I think it's about finding it's kind of like a product market fit as well. We hypothesize that, okay, this might be used for cold storage only, but once you start actually interacting with a wider group of people, you realize there are loads more problems with the current data storage solutions, and this might be one of the use cases where DNA data storage could come in as well. But what kind of impact do you think could come from research labs that are working on DNA data storage, and what role do you think they play in bringing such futuristic technologies to market?
Yeah, I think, topics like DNA data storage are really, these are the topics that I think are really on the scope of research, right? Because these are blue sky research topics that are high risk in the sense that nobody knows. I mean, we're all working on this together as a unit. We all want it to succeed, but nobody knows if it's really going to succeed. I mean, there's no certainty or there's no guarantee. And in fact, there are other initiatives also, right, in the area of digital preservation. A very famous example being Microsoft Research actually working once again on silica and glass for preserving data for a long time. And they've also demonstrated that glass can be used to store data using femtosecond lasers. You can etch data, you can etch patterns onto glass, which you can then read back by shining light on it, and then converting the images using machine learning techniques back into data. And I'm describing it very, very coarsely, but they are building a large scale solution using glass, right?
Yeah.
And so which one is going to work, DNA or glass? Nobody knows, right? I mean, it's up to, nobody can predict the future in that aspect. And I think this is precisely why research labs need to work on this, because these are the kind of cutting edge, high risk, high gain projects. If it works out, you are launching an entirely new data storage industry, which is great, which is amazing. And yeah, research labs need to work on this, because I think companies cannot actually invest the time and effort into something this speculative, right?
Yeah.
So you need research labs to take the hit when it comes to risk, to work on techniques that could potentially fail spectacularly, and yet they are going to contribute to the overall success of long-term data storage, right? So I
Yeah,
think
it's about
that's
building the
kind of
foundational blocks more than
indeed,
anything. Yeah.
indeed.
So this was one of the questions that I'm quite interested about as well, because DNA data storage is more or less just a decade-old field. And even if today we talk to people, and I specifically, when I tell people about DNA data storage, it's kind of taken in a very different perspective. They're like, "Oh, are you talking about big data? Are you talking about genomics data?" I'm like, "No, like storing digital data on DNA. It's as simple as that." So, what does your lab look for when they're hiring PhDs or postdocs? Because every time I speak with people and talk about DNA data storage, I get a very different response around it, and they kind of relate to everything else, but actually understanding that it's basically storing digital data on strands of DNA. So, like, what kind of people are you looking for when you're hiring PhDs or postdocs to work on these projects, and what would be the best way to reach out to you?
Yeah. Okay, so in the case of this thing, I was mentioning DNA data storage itself is actually a pretty interdisciplinary topic. So you need a consortium of people to actually work on this, and no single person can actually work on it on all possible aspects, right? Because there is chemistry, there is sequencing, there is biology, there is information theory, there is a whole lot of problems that are involved in it. So what I generally, in my case particularly, because I actually have the computer science background, in my lab I specifically look for students who have a computing background, who actually have worked on some aspects of data management, some aspects of systems, and who can expand out and then bring their background, bring their expertise to this domain, DNA data storage, right? And so that's kind of what I look for. But if you look at my collaborators who work on biology and sequencing, for example, they would be looking at people who are who have a biology background, who can actually work with sequencing instruments, who have bioinformatics knowledge, things like this. So it really varies. And my best suggestion for people looking for projects in DNA data storage is to look at these larger initiatives, the projects, and try to basically figure out where you fit within the consortium, what's your background, depending on that, and then to reach out to the people who are in your relevant background. And that's probably the best way to get an entry into one of these projects on DNA storage, right?
Yeah, absolutely. I think it's about making sure how your skills fit into the wider consortium or into the wider research area as well. But I'd like to kind of end this on a lighter note, which is more around what excites you the most about this field, and what do you think we could change in the current landscape to bring these technologies to real life faster?
Yeah. So what really excites me about this field is, well, actually the long-term storage prospect of it, right? And I think this is something that collectively, it's funny because as a society, we have this adrenaline rush, and so we are actually, predisposed to sort of look at things that are happening now, and this basically permeates everything, including research. So research is really focused. If you look at computing, for example, we are focused on optimizing performance down to the very, very last bit. How do you make things go as fast as possible? And I think DNA storage, this particular topic especially, it kind of asks you to take a step back, and it kind of asks you to look at, don't look at what's happening now. Let's think about the future. Let's think about, what's going to happen 1,000 years from now, right? Let's think of everything that could change potentially there. And how do you transmit something that you have today that's precious? And how do you ensure that something that's so precious remains safe over the next 1,000 years, right? And so it's really interesting. And I think the analogy that I like to think of is, if we had a nuclear winter and everything basically got destroyed, there in somewhere in there is an Arctic seed vault, which you might have actually heard of, which is basically a collection of crops, a collection of seeds that we need to repopulate it, that has been tucked away somewhere safe in the remote corners of the Arctic, right?
Yeah.
And they have a seed vault for preserving humanity's food supply in the future in case something goes wrong. I think we need something like that for digital data, particularly for culturally significant data. And there are a few initiatives that actually started similar to this. One of which is from this company called Pickle, which actually works on storing data on cinema film. They actually created a vault like this, a digital data vault, where they're actually storing data on film and then preserving the film somewhere, in the Arctic, right?
Yeah.
So I think it puts into perspective the fact that, it's a whole new line of work, a whole new thought process that forces you to think of the future. And I think that's what DNA storage really excites me about, is being able to come up with this medium that can really guarantee this intergenerational data transmission, right? And I think we don't have it today. Pretty cool.
Yeah. Well, DNA data storage offers a very promising solution to our ever-growing need for vast and secure data storage. And it's definitely proving to be a viable option for preserving information for centuries. And as we continue to explore the possibilities of DNA data storage, it is clear that this technology does hold a great promise for the future of information storage. But thank you so much, Raja, for joining us today and sharing your insights with us. It was great to have you on the show. And we do wish you every success in bringing this breakthrough tech to the market.
Yeah, thank you very much, Ishna, and thank you for having me on the podcast. I really think we need podcasts like the one that you're putting together to raise awareness about, the kind of things people are working on, particularly on the DNA storage front. And I think through your podcast, I hope that this reaches even a broader audience and more people get interested in this, right? So thank you very much for doing this.
Thanks, Raja. Thank you for listening to this episode of Dive into Deeptech MoSS, powered by HelixWorks Technologies and brought to you from Republic of Work Studio, Cork's leading innovation hub. Follow us for more updates. Until then, stay tuned.